let's look at one or two topics which are important, but then not very difficult to understand. First one is the concept called per unit. Are you guys aware of this thing? Have you heard about this? Have we discussed it in the class before? Any time? Have we discussed it before? Yes? When? Huh? Okay, that's good then. So what did we discuss? We discussed what is the base voltage, base current, base impedance, not. Okay, so what happens is you have multiple voltage levels, right? 33 kV, 11 kV, and you can have different power levels also. So usually people can either express it directly in terms of the actual voltage, actual power, actual impedance, or a simpler way is to represent all of these parameters in terms of per unit, right? Per unit means any quantity if it's x, so x in per unit is equals to the actual s. So any quantity x in per unit is given by x upon x base, right? So it's just that you can represent x per unit as a fraction, or you can represent x per unit as a percentage by multiplying it with 100, right? So that is a simple thing, there is nothing complicated here. Now only thing is that how do you define the x base? You can define it any ways you like, but then there are some standard practices how people define the base values. So if it's a single phase system, right, you have a single phase to neutral system, right, where the nominal voltage is V nominal, right, the power is P rated. In that case you define the bases as V base is nothing but V nominal. What is V nominal in a single phase? It's the phase voltage, right, RMS value of the phase voltage. 230 volt for instance would be the nominal voltage if I have to consider our room for now. The current base is, this is not P base actually, this is S rated. So I base is nothing but S rated upon V nominal. S base is nothing but S rated, and Z base is equals to, you can represent in any form you want, you can represent it as V base upon I base, or you can represent it as, I base is this one, so you can represent that as V base square upon S base, right. So voltage, current and power, if you have defined S, that means you have defined for both P and Q. For voltage, current and power we have defined the base values. Now if I have to say that this is a 10 kVA system, right, this is a 10 kVA system and load is consuming 5 kilowatt of power. It's a 10 kVA system and load is consuming 5 kilowatt of power. That means if I have to define P in per unit, what I am saying is it's a 10 kVA system, so divide S base is 10 kVA, right, which is S base, and it's, let's say, drawing 5 kilowatt of power, which is the actual power P, then the P in per unit is 0.5, right, and P per unit would be unitless as you can see. So it's just a way of representing, instead of calling it 5 kilowatt, I can say that power that is consumed by the load is 0.5 per unit. Is that okay? Similarly, if the voltage nominal is 230, the actual voltage you measure it's, let's say 115, then you say that the voltage is 0.5 pu. Is that okay? So you can apply, your X could be voltage, could be current, could be active power, could be reactive power, could be apparent power. For these three things you consider S as the base, this is V base, this is I base, and or it could be impedance Z and then you use Z base, right. So for example, if I connect load here of a certain value 1 ohm or 1 ohm plus 1 j omega, right? I can represent this in some PU form. So PU angle theta, I can represent it as that, right? How will I do it? This is the actual impedance Z divided by the Z base will give me ZPU, which will be real plus J times imaginary. So voltage, current, power, PQS, Z, all of these can be represented in per unit values. What is the advantage? It appears things will become simple if you are running some computational algorithms, right? Lot of times in general, like whenever you are writing any, let's say, embedded system program, so reality you would have a voltage feedback. If you want to control, for example, if you want to implement AVR, let's say in a microcontroller, right? Then you have to measure the grid voltage. Now grid voltage is maybe, there is some generator producing 22 kV, some generator producing 11 kV. So if you want to standardize thing, what you can do is you can do all the computation on per unit basis, right? And then you only need to multiply it with suitable scaling factors when you want to convert it into actual quantities, right? So you measure few things, convert it into per unit, then do all the processing that you want, and then finally again you can convert it back into real quantities, right? So it sort of becomes a more standardized way of doing things. That's one advantage of going into per unit. Another, so to say, advantage is as follows. Okay, let's say there is a source, there is an ideal transformer and there is a load, right? The source here is 11 kV 3 phase, so this is 11 by root 3 kV. So 11 by root 3 kV is to 230 volt, and these are the turns ratios. And then you have a load connected. Let's just say load is drawing a power of load is having a impedance of, or just a resistance of 10 ohm, right? Now in this case, if the way we have solved it, right, you can shift this resistance on the left side, then you can find the power, right, and you can find the current, voltages, whatever you want to find. If you want to do the same problem, but first you convert everything into per unit and then you can solve it, right. So what happens is, if there is a transformer, the per unit quantities on the left side will differ from per unit quantities on the right side. What I mean is, the base values are different because the nominal voltages are different. The power base may still be the same, but the current base and the voltage base will change, because one side you have 11 by root 3, other side you have nominal voltage of 230 volt. So let's just do this thing on a bigger board. So just redrawing the circuit. Ten ohm, 11 by root 3 is to 230, and let's say this source is also 11 by root 3. It could be something else also, but this is also 11 by root 3 kV. This is K 1000, right? Okay. So in this side, the base voltage is 230, right? There is, let's say this transformer is rated for, assume to be how much? Let's say 50 kVA, let's just take it 50 kVA is rated for 50 kVA, right. So the S base is 50 kVA, right, on the right side, and on the left side you have V base is 11 by root 3 kV and S base is same 50 kVA. What is the impedance in per unit value? What is this impedance in per unit value? No, just tell me the final value, right? Formula तो मुझे भी पता है. What is the final value? How much? 1.058. Okay, is that correct? Some of you are getting this value. So this is Z in per unit 1.08. There is no imaginary components. It's R in per unit. Is this matching? Okay. So this is ZPU. Generally, you would not expect ZPU to be more than 1. Why? Because if it's more than 1, that implies that the power this guy is drawing is more than the rated power, right? So if you calculate the power it is drawing, it is voltage 230 squared by 10, which would come out to be more than 50 kVA, right? Oh, Z base, no, I want Z per unit. Oh, Z base is this Z? No, I want Z per unit. Oh my God. Yeah. Is this sure? Did you calculate Z base everything correctly in terms of ohm, right? So it's coming out to be 9.45. Yeah. So this is a highly hypothetical example which I have drawn. Usually you cannot connect Z per unit 10 times or 9 times the base value. What it implies is you are drawing, actually the power drawn is 10 times 50 kVA, right, which is just absurd. So if you give me a chance again, I would just put a 0, one more 0 here, add one more 0 here, add one more 0 here, and make it. Is that okay? Just to make it a bit more practical then. Is that fine? Because Z base is V square by S, so I have increased S 10 times, so Z base will reduce 10 times. So, sorry, yeah. So let's just stick to the original value. I was wrong, let me correct myself. So we have 50 kVA system, Z base is something and ZPU is 9.45. Actually it's correct, so nothing is wrong here, my mistake, I sort of got confused. So if your impedance, if your rated, for flowing rated power, if you require, let's say hypothetically 1 ohm, then if you connect more than 1 ohm, right, you connect 10 ohm, then the power flow is less than the rated power. So it's perfectly fine, there's nothing wrong. So I got confused. No, not necessary. So that's what I'm saying, it's both is fine. You can calculate in percentage. Anything is okay. Somebody likes percentages, let them calculate percentage. Somebody doesn't like percentage, likes fraction, let them calculate fraction. 945%. Same as 9.45 PU. That's fine. Just jo karna hai karne do. Zyada tension mat lo. Let's come to the point. So now the point is, if this is the 10 ohm corresponding to 9.45, right? If you convert this 10 ohm, bring it to the primary side, right? And now if you calculate it in per unit on the primary side, can you quickly do that? How much would that value be? So you have still this source. I have bought this guy on the primary side. So this is 10 into N1 by N2 squared. So what is the per unit value of this one? Can you calculate what is the per unit value of this one? So same source, calculate the base, calculate the per unit value. Anyone got the value? What is the value? Nikal, Z base nikal. First find out what is the Z base. You know the power 50 kVA, you know the voltage base, Z base is equals to V square by S base. So calculate Z base, then divide that actual impedance by Z base. You will get the per unit value, right? Same. So you should get the same value. Okay? You should get the same value, right? And that's how we have defined the base, and that's how we have defined the turns ratio. So the idea is, now if you have a complicated system like this, right, with let's say multiple transformers, multiple impedances, leakage, magnetizing, everything, right? You have like a complicated network. So if you convert this whole circuit into PU values, right, then the whole circuit would just simplify and you can just remove all the transformers and keep all the impedances in PU. Right. So if you convert this normal circuit into PU values, you get a circuit without any transformer and all the impedance values in PU remains the same, because we have seen if you transfer an impedance from one side to another side, in the PU value it does not change, right. So that is in a way, I mean in a way another advantage, so to speak, of the per unit system. So that way if you have a complicated system of different voltage levels and so on, you can just simplify it and then now you can solve for it very quickly, right. Is that okay? That is sort of I think is the question 1 or 2 of your assignment. Because you got the same Z base, right, if you transfer it. So that means any impedance if you transfer from one side of the transformer to the other side, the impedance actual value gets changed by N2 by N1 square. But in PU, whether this one also whatever was the PU, here also it's the same PU, right. So you can just draw an equivalent with this, because voltage is anyways 1 PU on both sides, or if it's 50% it's 0.5 PU on both sides. You can just draw an equivalent circuit like this in per unit instead of drawing the individual transformers. Yeah, here everything we have converted to per unit, so you can just draw this in per unit. And then you solve for it and then you can convert back whatever you need. Okay, this is for single phase. For 3 phase also there is per unit system. The way base is defined is little bit different. Let's just have a quick look at that. So PU in 3 phase, V base is usually V line to line nominal value, right. V base is usually V line to line nominal value. So if you have 3 phases A, B, C, this is your V line to line, and let us say this is your line current. Then V base we define it as line to line nominal. In single phase we define it as phase voltage nominal. Current base we define it as I line rated. S base we define it as S rated. And these 3 values here are related, and you already know the relationship between these 3, which is S rated is equals to root 3 VL IL, right, IL rated VL nominal. Is that okay? So in 3 phase we already know, right, we use, instead of using phase voltage, we always use line voltage in communication also whenever we talk about it. So therefore the base is also I base, V base, I base and S base, right. Z base is defined as V phase upon IL, which is nothing but equals to V L to L upon root 3 times IL, which is nothing but equals to V L to L, this is rated or nominal. If I substitute from here, IL I am trying to substitute here, so it gets S times yeah. So Z base is defined as V nominal line to line upon S rated for a 3 phase system, right. So you can remember any of these 3 things and that is perfectly fine. What it means is, I mean that is a definition, of course you can say why are you defining it this way, I want to define it other way. There is no argument there, you can define it any way you want. That is the common practice how Z base is defined, which is V square by S. And now whatever we did for single phase, we can do the same things here with these new base values if you are doing a 3-phase question. No, configuration is anything. Configuration could be anything. No, that's why I am saying configuration could be anything. This is how we have defined the base. Actually, it could be star, it could be delta, it could be any connection. Hereafter, once we have calculated the Z base value, then any impedance you see in that network, whether it's connected in star, delta, series, shunt, open, anything, you just do Z upon Z base. So we have defined Z base. Now any impedance you see there in connected in whichever fashion, you just do Z by Z base, you will get Z per unit. Any voltage you see, whether that voltage is line voltage base, any voltage you see, you just divide it by V base, you get V per unit. Is that okay? So it's just the base values we are defining. Is that any question? Yeah. No. So again, if you remember, right, this is your system. You can have load connected in some fashion, source connected in some fashion, right? The way we are defining is this is line to line voltage and this is phase voltage, VAN. Now if load is delta, N will not connect. I would not call that thing as a phase voltage. That is not what I mean here. What I mean here is I am writing line to line by root 3. So even if you see right from the beginning, right, that nomenclature saying that delta is a phase voltage and therefore in delta connected system you have line voltage equal to phase voltage, that's the reason I am trying to avoid, because it does add to confusion. So what if you don't look at these two definitions, actually if you see in books and all, these two things will not be there. This is, I do it for my own understanding. You directly see Z base would be defined as V square by S. If that works for you, that's perfectly fine. But I just try to, in my mind, I try to look at it as, okay, if it's a star connect, that's how I remember it. If it's a star connected, then each impedance in star connected is nothing like base. So that's how I remember it. But you can directly use that. You don't have to look at this block. Now is that okay? So this definition is always valid whether you have star connected or delta connected.
All the utilities still have different values. How do you actually calculate what is the advantage? You need to take into account that based on solving the circuit.
Yeah, it's not much advantage, I agree. So what he is saying is that here you still have to convert each of them to Z base to bring it to this form, right? You could have just converted to a single side also. Yeah, you can do that also. It's the same effort, same thing. There's nothing much which changes here. I agree. Okay, so that was a small topic which we had to cover a little bit more detail, because any questions now if you see, especially in this assignment, you know, a generator question also where we were saying EF, VT, impedance, instead of defining it in ohms and voltages and current, one can just define it in base values, right? Okay, let's come back to the formula which we derived towards end of the last class, right? Which was for EF, excess, VT, the real power P was equals to EF is at angle delta, VT at an angle 0. So power is equals to EF magnitude into VT magnitude into sine of delta upon XS, and Q was equals to, what was Q equal to? Anyone? What was Q equal to? What was Q equal to? E cos delta minus Vt into Vt upon Xs. Is that fine? Just cross check, is that okay? The last lecture's note. Okay, so now these equations we derived, right? This could be a synchronous generator system, or this could be any system in a power grid, right? It could be a solar inverter producing an AC voltage connected to the grid. Is that okay? Let me repeat, just pay attention here. This is, what is this? This is, we derived it as a synchronous generator which has a synchronous reactance connected to an infinite bus. This could be a solar inverter which is converting DC voltage of the solar panel into an AC voltage connected through an impedance to the grid, right. This could be a battery storage where the battery storage is DC, then you have an inverter, that inverter connected through an impedance to the grid. Is that okay? This could be anything connected on the grid practically. So, this is a very common use case. This could be actually one bus here as compared to another bus 100 kilometers down the line, and then a line connecting between these two buses or these two substations, where we have modeled the line as only inductive line. So, this is a very generic diagram, right. We derive it using first time we see it in synchronous generator, but this is a very generic diagram, and as we would see later, this gets applied in lot of places. So, these two equations you will keep seeing back again and again. Just remember that these equations we assume there is only excess, we neglect the resistance, right. In reality there may be resistance also. You can of course derive the formula, there is no big deal in deriving it, but then yeah, most of the times we ignore it and we just work with these equations. Is that okay? Any doubt in this part? So, this could be lot representing lot of systems, right. Okay, if that is okay, let us just focus on the first equation. So, if you see the first equation, this is your Vt at an angle 0 and this is your Ef at an angle delta, right. Here delta is positive, so I am assuming your Ef is leading Vt. So, now if delta is 0, right, if delta is 0, then what is the power transfer from Ef to Vt or Vt to Ef? 0, right. So, if delta is 0, power transfer is 0, correct. So, if I want to transfer, let us say 100 kilowatt of power from this source to this source, right, what should I do? I should ensure that my delta is leading by some degrees, so that the power transfer is 100 kilowatt. Is that okay? So, if I want to transfer 100 kilowatt from here to here, let us say these are two big generators running far apart, there is a line which is interconnecting them, and they have their local loads also, right. I want to transfer 100 kilowatt from this generator and load or this city to this city. What should I do? Somehow I should try to lead this voltage by a certain angle which corresponds to that much of power transfer. Is that okay? Not okay? Do you want me, anyone wants me to repeat this sentence? Yeah, so as you sort of see later on in more advanced courses, that 90 degrees is too dangerous, because once you go on the right side of the 90 degree, everything changes. So usually you try to keep excess such that you operate within a small band, let us say plus minus 20 degrees maximum, right, if not less than that. You do not go into extreme cases of 90 degrees, right. So you can have, this has 10 degrees, 15 degrees, you can access, you can tune it accordingly. So you will achieve the rated power flow. You have to keep excess also small, which we anyways want to do. I mean, we want to keep excess small, right. What is your doubt? Okay. So in this case, this is P is positive if delta is positive, right. If delta is positive means Ef is leading Vt. So the source which is leading will supply active power to another source which is lagging. Okay. Now imagine if this is your grid and this is an inverter connected to a battery. So this left side is something like this. Yeah, left side is this, right side is of course the infinite bus or the grid. You remember that circuit, right? You remember that circuit? That was the edge bridge inverter which we have studied a few lectures before. You remember we can do sine triangle modulation of this and we can generate a voltage here, let me call it V alpha, which looks like these PWMs and so on. But if you do the Fourier series of this, what you see is there is a fundamental component in that. You remember that? Right. So now what is this? This V alpha could be your EF. It has high frequency sources, it has low frequency. High frequency, of course, this impedance value would be very, very large, right. So high frequency, even though there is a voltage of high frequency, the currents may not necessarily flow too much, right, and there are other ways of suppressing it. We can increase the frequency to an even higher value, that will offer even higher impedance. So if we ignore the high frequency phenomena, if you see, this is nothing but the output P alpha, right, and now you know that if you do sine triangle PWM, SPWM, right, then you can control the carrier. You remember the carrier, you have to remember all of those things. So you had a carrier and you had a, you had a carrier and you had a reference, right. So now reference, you can change the angle of the reference, you can change the magnitude of the reference, which would change the angle and magnitude of fundamental component of V alpha, right. Let me call it V alpha 1, and which would change this angle and magnitude of this source, which is, in this case I have written EF and delta. So if you want your battery to supply to the grid real power, you can change the reference sinusoidal so that the angle is leading then the grid voltage. So real power will start flowing back. If you don't want to flow so much of power, okay, reduce the angle a little bit and maintain it, whatever power you want to give it to the grid. You want power to be drawn from the grid, then you just make the angle, you make delta negative, right. You make this guy leading and this guy lagging, so power will start flowing back. Is that okay? Correct. Okay, how many of you remember this? Please raise your hand. अच्छे से उठाओ. Okay. So you remember we had a reference waveform, we had a carrier waveform. Were we calling it reference or with some other name? What were we calling it, reference or something else? Reference. Okay, some people are saying reference, some people are saying modulating waveform, modulation signal. Yeah, whatever. नाम में क्या रखा है? So reference was, if you remember, it was m sin omega t plus delta, right, where m was between plus and minus 1. You had omega, which is fundamental frequency, and you have delta. Fundamental frequency was much higher than the carrier frequency. So if you were using this, then we saw that the voltage produced across V alpha, the fundamental component of that voltage produced is nothing but m times VDC into sine of omega t plus delta, right. This we have derived. The fundamental component V alpha 1 is nothing but m times VDC into sine of omega t plus delta. So therefore, by controlling this reference waveform, by adjusting m, you can adjust the EF. By adjusting this delta, you can adjust this delta, right. Is that clear now? Any doubt? Okay, so this is okay, this is clear. So any source you see, anything connected to the grid, be it storage, be it solar power, be it a wind turbine, be it a hydro, be it a steam turbine, be it just analyzing two different points in the grid connected through a line, this kind of architecture is very, very common. So whichever source is leading supplies power, whichever source is lagging absorbs power. Okay, if this part is well understood, let us go and look at this part. Okay, before we do that, the first part, sine delta, since I told you that usually delta is small, there are some concepts which does not allow us to keep very large value of delta. Those concepts we don't study in this course, we study in a bit more advanced course. Nevertheless, since delta is small, sine delta is almost equals to delta. So a lot of places you can also approximate this as, instead of sine delta, you can write it as delta if delta is small, of course in radians, not in degrees, right. Okay, so if this first equation is done, let us look at the second equation. No, excess you cannot keep track of excess, you can design excess, but once the design is there, once you have fixed the line or fixed the inductors or something, then excess is fixed. At the design stage, you can do the calculations and you can make out, okay, this is the power I want to transfer, this is my maximum delta I can go. So, I should make sure that my excess is this or less than this. So, I should design my system accordingly. That I can ensure, but you cannot do anything once it's fixed. Okay, so initially it was of course not possible, right? So, fixed capacitor, fixed inductor, everything is fixed. Now, since you have more power electronics, you can, for example, switch few inductors on and off, you can switch few capacitors on and off. So, there is a whole range of devices which are a combination of these passive devices and some active devices, maybe MOSFETs, maybe IGBTs, maybe thyristors. Together they can offer you some controllable inductance and capacitors. There's a class of it, it's called as FACTS, Flexible AC Transmission System, FACTS, right, FACTS. So, there is, if you search for flexible AC transmission systems devices, you would see a host of devices which can do lot more things, right. Later on if you want, you can do a course in FACTS also, right, to learn more about that. So, yeah, it's possible now of course, but it's expensive nevertheless. So, initially power is 0, but once you are connected, now you can change the delta and you can flow the power you want. Okay, if you look at the second equation, it defines the reactive power, right. Here you see usually if delta is small, then what will be cos of delta? If delta is small, cos of delta would be 1. So, you imagine Q is equals to Vt upon Xs into E minus Vt, right. As you can make out, an easy way to control it is the magnitude of E and Vt. So, if this case again, if Vt is the infinite bus, you do not have any control over Vt, but you can change Ef. So, if you make Ef equals to Vt, Q is equals to almost 0, right. Ideally 0, in real life it may not exactly be 0 because this is not exactly 1, neither this is pure excess, right, there is a small r also, but ideally 0. If you increase Ef, if you make Ef more than Vt, Q is positive, that means the reactive power is flowing from this source to this source. If you make Ef less, Q is negative, that means reactive power is flowing from this source to this source, right. So, by using magnitude of E, which again you can control using in any source, using sine PWM if it is an inverter based source, if it is a synchronous generator you can control E using, if it is a synchronous generator you can control magnitude of E using field current, right, field current. If you provide more field current, you have more E is equal to 4.44 NF phi m, right. So, if it is a synchronous generator, you can control E using field current. If it is a power electronic converter, you can control E using the reference waveform, right. But either way, you have control over E and you can control Q flowing in either direction. Any question, any doubt? Yeah. Yeah, correct. In context, if you, because there is always an excess here, right. So, if what he is saying is, okay, let me just think over it. What he is saying is, if you have a current here and if this current and this voltage Vt makes an angle 0 degrees, right. So, that means the current that I am supplying to the grid is at unity power factor. In that case, you are saying that you cannot transfer any real power. Why are you saying so? Okay, let us draw the phasor diagram and see if that is true. So, this is your Vt at an angle 0, you are saying your current is also flowing at same angle 0 with respect to Vt. So, your excess voltage across excess V excess is like this is your V excess and therefore your EF is this, which is at an angle 0. You can, why you cannot? You can. No, initially you said power factor. Yeah. So, delta, remember delta is not the power factor, Delta has a different name. What is delta called? Delta is called as power angle, right? Delta is called as power angle. So, good you asked this question. So, delta is not power factor. Power factor is the angle between voltage and current, not between two voltages. Delta is called as power angle. So yeah, if delta is 0 then P is 0, yeah, of course. Any other question? Any other doubt? Okay, yeah, that's a good question, and that is a question which takes our next half an hour. Why do you want Q to flow from either side? Why do you want Q to flow from here to here? Why do you want Q to flow from here to here? So, if you are a source, right, I am a source, maybe I am a synchronous generator, right, there may be lot of inductive loads connected further, right, and to supply that Q, you can connect lot of capacitors, or as a source I can produce and give that Q to them. Now you have to decide which one you want to do, whether putting capacitors is cheaper or oversizing the source and producing less P and there is some amount of Q is cheaper, or you usually do both, a combination of both the strategies, right. Similarly, you have connected lot of capacitors and suddenly all the inductive load turns off. Now who will absorb that Q, right? So you absorb that Q. So this is basically, yes, you would like to minimize it. I mean, if you have a generator, if you have a big power generator, you would ideally want it should produce maximum amount of P, right? And Q should be somehow be able to manage it, but it has a flexibility. So if whatever surplus Q required or to be supplied, it can manage. Correct. No, you don't do it manually. None of these things is done manually. Actually, manually you cannot control, things are so fast. So these are all done through some control system. There are, lot of control algorithm which goes into that, but put in a very simple way, this is what happens, E and delta, right? But in reality, yes, it will be done through some complicated control. Okay, now let's go to the question of reactive power. Okay, let's just see a little bit about the transmission lines. You have seen how the power is being distributed over longer distances, right? If you are driving on a highway or something, you would see there are these huge overhead lines which are going over long distances, right? So based on the length of the cable, generally we categorize these transmission lines into three categories: short, medium and long, right? So we say you can have a short transmission line, you can have a medium transmission line, or you can have a long transmission line. Now if you ask me honestly, what do you mean by short? 1 kilometer, 2 kilometer, 5 kilometer, 10 kilometer. There are, of course, in books and references, if you Google, you will get some sort of boundaries, but these are all very flexible boundaries, right? So usually I think maybe short maybe about 50, 100 kilometers, medium maybe about 100, 200, 300, 400, 500 kilometers. Anything beyond that probably would be long or something, right? So these are all rough boundaries. There is no very, sort of hard and fast cutoff there. But why we are categorizing into these three is as follows. If you have a short cable, right, then usually what happens is when you have a cable, there are these inductances and resistances, right, and also because there are two lines, they form some capacitance between them, right. So if you have an overhead line, they have a series resistance because of the cable conductor, right. They have series inductance because of the loop between the plus and the minus, right. And because there are two conductors, whatever be the distance, there is some capacitance between them. So usually you have shunt capacitors, you have series R and L. Is that okay? Any line which you take, you will have these things, values would of course change. So if you consider a short line, what people do is, because it's short, there is not too much of an overlap, so people would forget about these capacitors and people would just represent it using a series L and R, right. In reality, this L and R are distributed over the length of the line, let's say over 20 kilometers. You can just represent it as a bulk parameter, right, as a lumped parameter you can represent it. So you can represent just L and R as a lumped parameter. Lumped means you have just written one R, one L and you have sort of modeled it. Now you can use it in circuit simulation, you can write differential equation, you can do whatever you want to do. If it's a medium line, you can no longer ignore the capacitance. So therefore, there are two models, one is called as a pi model, one is called as a T model. The pi model is like this. So you have L, R and C, and in T model you have like this. So L and R you split on both sides and in between you have a gap. Again these are lump models, the whole line will have C throughout the line, but you just put all together, you calculate it, you put at single place. In T you put it at one place, in case of pi model you put it at two places. So you have like an equivalent circuit of the line. Why? Oh no, in reality you don't have two lines, you have three lines and these are equivalent, these are single phase equivalent circuit in a way. Is that okay? Then you can have a long line. In long line, the modeling is bit more complicated. You don't usually use the lump model approach. So you have a distributed LRC which continues to run. There are multiple blocks of LRC and then you have to write the equations for those. So if you want to read in more detail, you can go through that, but we are not going to do too much about those distributed modeling. So we are not really touching it. You can imagine long line is like lot of combinations of these pi models, so to speak, right? Lot of series combinations of these pi model or T model. Any question? This is just a knowledge, there is nothing much to understand here, but you should know about this. If you have a cable versus a line, right? What is a cable? A cable is where you have plus and minus, or you have three wires if it's a three phase, all very closely packed through insulators, and then overall there is an insulation, and this is what we call it as a cable. A line means they are mounted up, they are going ahead, there are no insulations, air itself acts as an insulator, right, and they are placed far apart from each other. So that is a line, this is a cable. Is that okay? These are all parasitics here, all the L, R, C are parasitics here. Yes, but it's AC, so it's AC. Yeah. So in reality there is one, but because if the distance is so small, the overlapping areas may be so small that the values may not be something which you consider about. That's the only thing. But reality everything is same, right? Just not that if you have made it longer line something has changed. It's only the values are small and therefore you can ignore it. The impedance will be 1 upon j omega c. If c is too small, you can avoid this shunt branch. Okay, cable versus line. So cables is something where you have packed all the three phases, everything together, and line is something which are like overhead lines, right? Now let me ask you a question here. How does power gets distributed in our campus? Is it through lines or is it through cables? How many of you say cables? Raise your hand. Cables. Okay, how many of you say lines? Raise your hand. Lines. Okay. Have you seen any line in campus? I have not seen any. Yeah, underground cables. So the things that run underground are essentially cables, right? If you go near to any of these distribution box, right, those red colored painted box, there are these huge cables coming out from the ground and then again going in, right? So those are cables. So cables are usually underground, the lines are overhead, right? In distribution system, when you are distributing power to the customers, right, you prefer to use cables instead of using lines, because what happens is these distribution lines are not very high up. So for example, if there is a storm and there is a tree which falls on the line, then it creates a fault and the whole power goes out, right? And that is the reason when I was small in our where I used to live, we of course had distribution, using overhead lines, not through cables. So even if there's a little bit of cloud and then one lightning strike and then power just goes off, it was a default setting, right? That, and probably it was not that fault was happening, maybe it was a precautionary step, because if there's a fault happens, it may cause more damage, so somebody would just turn on the supply to avoid that, maybe, I don't know. But if you have cables, which is the practice now, then you don't have to worry about those things, right? Now that said, if cables are in a way better, more reliable, right, then why don't we do the long power transmission also using cables? Why don't we do that? Why do we have overhead lines when we want to transmit power from one city to another? But within a city, you have cables. If you go out now in Mumbai, right, you would see cables, you don't see overhead lines. But why is it that if we want to do power transmission over longer distance, you still use lines? Yeah, maybe. Maybe she's saying that you have to dig it, you have to put it inside.
No, not that. If you space the wires and the lines, because there's a lot of current, you want to avoid it.
Or do you mean that you have lot of voltages among the two cables? In distribution you have 11 kV, in transmission you may be doing at 400 kV. So between the two cables, between the two conductors, you have to have large insulation. You would have to use very, very thick insulator, sort of material between the two. So the cables may become just too big, very expensive or something like that, right? So yeah, there may be some economical factor, of course, coming into picture. But any other reason? Capacitance? What about capacitance? 1 minute, उसको बोलने दो पहले. Go ahead. Okay, yeah. So this is one point which we'll explore in some time. What he is saying is, I'll just repeat, that if you have a long transmission line, long means you can have in any of these categories, right? You have 50 kilometer, 100 kilometer line. In that case, in cables, because the two conductors are very close by, yeah, C is epsilon A by D, right? If D is small, C is large. So in cables, since you have two conductors very close by, you have large value of C's, right, and relatively smaller values of L and R. But in, so therefore, in cables, you have large C, right, but in line, you don't have large C, right, and this leads to something, and I will talk about it very, very soon. So just give me some more time, I'll talk about it. But meanwhile, let's gather a few more reasons. Bol bhai. Absolutely, yeah. So if you want to do 400 kV transmission cables, you have to have huge insulation. Air, fine, you keep it 100 meters apart, you keep it whatever, or X apart, you keep it 2 point X apart, right? You just have to keep increasing the distance. The air itself acts as an insulator between the two conductors. So maybe economically also it probably makes sense to use lines instead of cables when you want to do transmission over a long distance, right? Okay, coming back to this reason. This is the reason I want to latch on to. So let me explain you what this reason means. Yeah, but then you have to know what is the insulation of the ground. Typically, ground does not have much higher insulation, na? But ground is a good conductor, so to speak, over a longer area. So okay, now you have to answer these questions, huh? Okay. So you have a source which is V1 delta 1 and you have an excess and you are the end of the line, this is a line I have modeled as only as excess, let us say for now. End of the line you have V2 angle 0, alright. If I don't connect anything on this side, there is no load connected here, what will be V2 angle 0 relative to V1 angle delta 1? They will be They'll be, if I don't connect any load here, what is V2 angle 0 versus V1 angle delta 1? If I draw the phasors, how would they look like? They will be equal, na? Kyun bhai? Isn't that okay? Okay or not okay? Okay, na? If you don't have any current in the line, then this is same as this, right? This is same as this. Now, if you have a load here, then this will change with respect to this. Imagine I have connected only a capacitor here. I have not connected anything, I have connected only a capacitor here. Right? Now, we will try to plot the two voltages. So, how would it look like if I start with V2 angle 0 as my reference, right? Then the current that is flowing will be capacitive, so current will be leading. So, my current is IC is leading V2 angle 0, right? And if the current is leading, the voltage across inductor is V of XS, which is further leading. So, this is my V of XS, and therefore my V1 is this phasor diagram looks okay? Inductor voltage is leading the current by 90 degrees. So, Vxs is nothing but 90 degrees ahead of IC. Is that fine? So, what does it mean? It means that your voltage at the receiving end of the line, it is a line, the voltage at the receiving end of the line could be more than the voltage at the sending end of the line. Voltage at the receiving end of the line could be more than the voltage at the sending end of the line. Is that okay? Which is a bit surprising. I mean, you would not expect it. If you have a generator, if you have a source, let's say you have a DC source, now you have two lines coming from there, I have connected a load here. If you measure the load voltage, it will be less than the source voltage, no? Of course, because there is voltage drop across the line. But here, you have 200 volt here, and now here you are checking, you are getting 250 volt. This is a bit of a surprise, right? Is this diagram okay? Anyone want to have a quick look at it, cross check if we have made some mistake here probably? It's a bit unusual. I mean, we don't expect it, at least in DC systems. So, in DC you would not imagine it, in AC it can happen. So, if you have a load, if you have a light load condition or you have a lot of capacitive kind of load, your voltages here could be very, very high, right? And this capacitor could be the one capacitor which you had connected in the load side to compensate for the inductive load that you generally have. But let's say aaj inductive load off kar diya, raat hua inductive load off kar diya. So inductive load goes off, so that compensation has no meaning now, but your capacitor is still stuck there. So now what will happen in night? You may see much larger voltages here than what you expect, right? This could be one reason. The other reason is you are using a cable, and in cable you have large value of capacitance, right? If you use pi model, you can model it two capacitor, one here, right? So this could be the capacitor of the cable itself. Especially very long distance, let's say 200 kilometers, 300 kilometers cable, you would have huge value of capacitance, right? So this phenomena is called as, it has a name, Ferranti effect. It has a name, Ferranti effect. What it means is that your load side, we also call it as receiving side, voltages could be more than the source side or the sending end voltage. Is that okay? So your load voltage or the receiving end voltage of the other side of the line could be more than the source or the sending end voltage. If you have this condition where there is a large capacitor, this condition can occur in two ways. It could occur in multiple ways, but very two ways you can very simply correlate is: one, you were using a cable with a large capacitance, Two, you are using an overhead line, but now the distance has become so much that still the capacitance has become large, right? Three, when it's a short distance cable or a line, but you had some capacitors actually connected here to compensate for the inductive loads, but those inductive loads are turned off. Maybe that industry in night shuts down, right? Now you have these excess capacitors sitting there, so they would lead to the same phenomena. So it could be, let's say, these 2 or 3 reasons, right? And the name for this effect is called as a Ferranti effect. So any doubt in this? Any doubt in the Ferranti effect? Any doubt in Ferranti effect? Okay. Now there are two things here. One is, of course, that we have the load voltage is more, right? That is one problem. The other problem is, even if you don't have any load connected whatsoever, right? Your line is loaded with some current because of this capacitor. If you don't have this capacitor, the current will be 0, right? Because you have a capacitor, your line is loaded, and this is eating up some of the capacity of the line. In fact, if you remember, that is the reason we said lagging power factor is bad in the previous course in the beginning. You know, you remember we said lagging power factor is not good. Why? Because lagging power factor means you have some current flowing in the line, which is unnecessarily eating up the capacity of the line. The line could have supplied more active power. Now you imagine you are doing high voltage AC transmission over long distance, right? What will happen? You will have enormous amount of capacitance. Is that okay? And that capacitance will continuously draw some reactive current. So your part of the capacity will get wasted. And that is the reason you generally move from high voltage AC to high voltage DC, because in DC that capacitor actually doesn't create any problem, right? There is no reactive power there. That's the motivation for going for high voltage DC transmission, right? If you want to transmit over very long distance, you move to high voltage AC. If you want to transmit for medium range, you use overhead line. If you want to do distribution very small distances, use cables in AC, right? And that's how all the three have been set up. Any doubt? Oh, HVDC you transmit DC voltage, right? So DC voltage you transmit over capacitance, over you have capacitance, they will charge once, but then they will remain charged. They are not drawing your current continuously, right? So in DC, the capacitance are still there, but those capacitance will just charge once and then they will remain. They will not like keep on drawing some current. Unlike in AC, the same capacitor keeps on drawing reactive current, right? Any other question? Ferranti effect and niche. Why we move to HVDC is predominantly loading of the line and maybe partially Ferranti effect, but predominantly loading of the line. Ferranti effect will also kick in if you have light load condition. If you have light load, Ferranti effect will kick in, but even if you don't have light load, if you have full load also, still this capacitor is loading the line, and that's the primary reason we move to HVDC. Otherwise, you can use FACTS, right? You can use FACTS. You can have some sort of an inductor connected in parallel through some switches. You can actively control. So now the question is, which is cheaper, which is expensive, and then finally, you take a call. But for very high voltage, long distance transmission, therefore people prefer HVDC. If you have, we talked about offshore wind. You remember we talked about offshore wind. Offshore wind. Offshore means there's a wind generator, but not on the land, it's in the sea, right? And a lot of European countries have huge amount of offshore wind. So there is a generator which is producing voltage there. Now that power has to come to the land for it to be used, right? How will you bring that? That's an AC power because it's some sort of a rotating mechanism. So how do you bring that AC power to the land? You can have overhead lines, but overhead lines building in sea would be quite challenging, right? On land you can do it, but overhead lines on sea would be quite challenging. So you use cables, right? Because you use cables and you try to bring the power, you have the same problem. And therefore, there are people who talk about that you can connect the offshore form using some sort of an DC instead of connecting using AC, right? For the same reason, because cables, you would not use for anything longer because of the excess loading of the capacitor. So there are a lot of, with the same principle, there can be a lot of reasoning and a lot of thoughts can get connected. Last question for today. Yeah, that is a separate topic. We can talk about it separately. See, what she's saying is there's wave power also, right? People use wave power to generate electricity. Yes, there are a lot of them which we did not really touch upon in this course. There's geothermal, there are a lot of things. Yes, those are there and they do contribute little bit now, maybe in future they may contribute, but yeah, that way you put a wind farm right in the land itself, right? Why are you putting it in the sea? You put a wind turbine on land, why are you putting it in the sea? It's about money, right? No. So the how it works is it has to be economical, and being economical, there may be some technical challenges, right? And then we have to solve those technical challenges. The fundamental thing is it has to be economical. If it's not economical, it doesn't make sense. So, okay, I think any other question? Any last question? Okay, so we stop the lecture. We stop the recording.